How can black holes be hot when all they do is suck in everything around them? Why is the Oort cloud so perfectly spherical? How do astronomical measurements work? And in Q&A Plus, can small moon impacts be a threat to Earth? All this and more in this question show. It's time for the question show. Your questions, my answers. As always, wherever you are across my channel, if a question pops in your brain, just write it down. I'll gather them up and I will answer them here. All right, let's get into the questions. Mist Solar. The Oort cloud visualization is almost always a perfect sphere. How does it keep its shape when interacting with other nearby gravitational objects and radiation while traveling? Yeah, so it's interesting when you see, we have the plane of the ecliptic, or we have the way all of the planets are lined up around the sun. That, obviously the sun formed from this nebula, the protostellar nebula. It spun up, flattened out, and then in the protostellar disk, the planets started to form. They gobbled up additional material, cleared out their orbits, and now everything is all lined up. But when you look at the illustrations of the Oort cloud, they're not lined up. They're more like this big sphere. And we know that the Oort cloud is a sphere because long period comets come from everywhere, come from all directions. They come randomly into the solar system. And they're not coming from along the plane of the ecliptic in the way that all of the other objects that we're familiar with, like the Kuiper Belt object, it's lined up around the solar equator, all the planets, all the centaurs. But no, the long period comets come in all directions. So why is that? Well, when you are in the Oort cloud, you are really far away from the sun, that your orbital velocity around the sun is very, very low. So Mercury is going at 48 kilometers per second around the sun. Earth is going 30 kilometers per second. Once you get out to Neptune, you're going 5 kilometers per second around the sun. And once you get out to the Oort cloud, you are going much slower. And that means the gravitational interactions between other Oort cloud objects can change your orbit. And so you have two Oort cloud objects that get relatively close to each other. They sort of tangle gravitationally, and then they go off in new directions. And so over time, over billions of years, that starts to make the Oort cloud more and more spherical over time. But there are some large-scale structures in the Oort cloud. So there was a paper that came out a couple of years ago, and we reported on that in Universe Today, that there are these sort of various donut shapes in the Oort cloud closer in to the solar system. And there's sort of structures in the outer Kuiper Belt. But once you get out to the very limits of the Oort cloud, you're really at the very limits of the sun's gravitational influence in its local environment, that these objects, these icy objects, are just one bad day away from drifting out of the sun's influence and being caught by some other star. And that's how you get interstellar objects. So they just interact just gently with each other and go into a more spherical form around the solar system. Arjun, could we detect the Oort clouds or Kuiper belts of exosystems? So astronomers have detected the Kuiper belts of exoplanetary systems, and they're ridiculous. Like, they are solar systems that are extreme compared to the solar system, that maybe there was some kind of large icy object that was shattered recently, and so they've been able to see this giant ring of icy material around some other star system, but not an Oort cloud. That has never been seen. I mean, we haven't seen our own Oort cloud yet, but people have seen the equivalents of Kuiper belts around other star systems. The film, how hot black holes are. So the question I think you're asking is, how hot are black holes? And there's sort of like two answers to this question. So the first answer is the environment around the black hole. So not the black hole itself. So, black hole is obviously this mass that has been compressed down to some ridiculous amount. It's surrounded by this event horizon, and the black hole is spinning. All black holes seem to be spinning, and they're often spinning sort of at the maximum rate that they can, sort of like 65% the speed of light as they're rotating. And they're surrounded by this sort of twisted space-time, very powerful magnetic fields. Magnetic fields are interacting with the material that is trying to fall into the black hole, the accretion disk around it, and that gets compressed and heats up to millions of degrees. So you've got this environment around the black hole where stuff is heating up. It's kind of like the interior of a star. It's shining with X-ray radiation that you can see with space telescopes. It's as if you were looking into the center of a star. And in fact, around the biggest black holes, they're actually creating new elements in the accretion disks around them because of this star-like environment that is around the black hole. But that is not coming from the black hole. And people say, like, why can there be radiation coming from a black hole when nothing can leave the black hole? Well, it's not coming from the black hole. It's coming from the environment around the black hole. The black hole spinning, interacting with its environment. You get these jets and winds that come out. And if you're staring right down the barrel of one of these jets, that is a blazar. And then if you're seeing it a little off to the side, then that's a quasar. And you are seeing this super bright jet of material that is coming out of the star. Sort of a classic example. If you look at M87, which is one of the supermassive black holes that was seen by the Event Horizon Telescope, you can see this jet of material that is coming out of the black hole. It's amazing. So that is the temperature of the environment around the black hole, but that's not the temperature of the black hole itself. Black holes absorb everything that falls into them, all of the matter, all of the energy, and nothing, not even light, can escape the black hole. Not even radiation. Radiation is just light. It tries to move at the speed of light. You have to go, even moving at the speed of light, you cannot escape the grasp of a black hole. And yet, black holes have temperature. And this is sort of this incredible realization made by Stephen Hawking, like back in the 1970s, I think, that he figured out on sort of the way black holes work and the way they interact with their environment, that you would actually, an outside observer would measure radiation coming off of a black hole that radiation has to come from the mass of the black hole, that there's no other way that you can get that radiation. It has to come from the black hole. And so in order to be able to give off radiation, to give off heat, the black hole has to evaporate. And the temperature of the black hole depends on the mass of the black hole. When the black hole starts out, say it's something that is 1 billion times the mass of the sun, like a supermassive black hole, then it's going to have a temperature that's just like a tiny little bit above absolute zero. But as it evaporates, it gets hotter and hotter and hotter. And eventually, when the black hole has like the mass of a mountain, it is glowing in X-rays, super bright, and then eventually it just sort of explodes in this puff of gamma radiation because it's just gotten so hot. But the evaporation of the black holes depends on the ambient temperature of the universe itself. Like right now, the ambient temperature of the universe is 2.7 Kelvin, so 2.7 degrees above absolute zero. And so right now, all of the biggest black holes are absorbing radiation from the background temperature of the universe. But over time, as that background temperature cools down, eventually it will go below the ambient temperature of the black hole, depending on its mass. And then the black holes will start to evaporate and eventually fade away after a Google years. It's time to shout out all the new $5 patrons and above: Cass, JV Static, Brian Joy, Doug Hilton, Jason Weitzel, Daniel Lebold, Stephen Branca, Bear, Jody Hoff, and Tekon. Join the club at patreon.com/universe today. DO6769. Astronomical measurements. What are the various units and how do they relate to each other? I know light year and AU, and then there are some ladder stuff and redshift stuff thrown in. Thanks. I mean, there's like two parts to this, right? Like, what are the different methods that astronomers use to measure distance in the universe? And then what is the methodology that connects those measurements together? How do we know how far away things are in the universe? So I'll tackle them sort of one after the other. The first thing on the sort of methods of measurement, I mean, obviously you can measure things in kilometers, you can measure things in hundreds of kilometers, millions of kilometers. The moon is 400,000 kilometers away. The Earth is 150 million kilometers away from the sun. Jupiter is like 700 million kilometers away. I forget the exact numbers for some of these. And so an astronomical unit is the average distance from the Earth to the sun. It's like 149 million kilometers on average. And so instead of just measuring in hundreds of millions of kilometers, you can just say, how many astronomical units is it? And so now you can measure things, 10 AU. 50 AU, 50 astronomical units. And so the solar system contains, or will go out to say, tens of thousands of astronomical units away, which is sort of where the outer limits of the Oort cloud are. So even, the entire distance from the Earth to the sun just becomes one of tens of thousands. And then of course, light years. It's the distance that light travels in 1 year, but you can have a light second. The moon is about a light second away from us. You can have a light minute. The sun is 8 light minutes away from us. It takes 8 minutes for light to travel from the sun to us. You can have light hours, light days, and of course, light years. And a light year is 4 quadrillion kilometers. I apologize if I'm just sort of doing this off the top of my head. But like the nearest stars are like a little over 4 light years away from us. So it takes 4 years for light to travel from us to the nearest star system. And then the system of measurement that most astronomers use is the thing called the parsec. The parsec is it's a very weird measurement, but the gist is that when you sort of define an angle to an object in the sky, and then you measure the angle to that thing when the Earth is on one side of the sun, and then 6 months later, the Earth is on the other side of the sun, the thing that you're looking at will move back and forth in the sky. And this is the technique of astronometry. And you can essentially do trigonometry to find out the distance to that object. And sort of the classic example, of course, is you hold your thumb out at arm's length, and then you open up one eye at a time, and you watch as your thumb jumps back and forth. You could calculate the distance your eyes are apart just by measuring how far away your thumb moves. Or you could calculate the distance to an object. You could calculate the distance to your thumb purely by measuring how far it jumps back and forth using trigonometry. So, all that math that you learned in high school is actually super useful. And so this measurement is called the parsec, and it's a little over 3 light years. And I forget the exact, it's like the amount that an object travels back and forth, and I forget all of the different pieces. But parsecs are done using that trigonometry, and it's a little over 3 light years away. And then astronomers will have kiloparsecs, so thousands of parsecs, and then they'll have megaparsecs and even gigaparsecs. And then the last measurement tool that astronomers use is called redshift. And you'll see like a Z equals something number. And that is essentially the speed that this object is moving away from us, because thanks to Hubble, we learned that the farther away something is, the faster it's moving away from us. And so astronomers will measure the redshift. And redshift 0 is a few billion light years away from us. Redshift, say 13, is stuff that is seen when the universe was around 300 million years old. Redshift 1000 is the cosmic microwave background radiation. And so astronomers will typically, once things get really far away, they'll just define them in terms of redshift. And you can convert redshift into tens of millions of light years or hundreds of millions of light years or billions of light years. The problem is that the distance doesn't make sense anymore because you're moving, they're moving, and the universe has expanded in between in the billions of years that these things have existed. And so, often people will say, well, astronomers are looking at a galaxy seen when the universe was only 1 billion years old. And so that galaxy is 13 billion light years away. And not true. The galaxy is actually not 13 billion light years away. That galaxy is probably more like 20 or 30 billion light years away today, but the light has been traveling to us for 13 billion years. And so that's why astronomers switched to redshift, which is the sort of like one number that uses all of that. So that's like the distance tools that the astronomers use to sort of talk about distance in the universe. And then the second part of your question is like, what are the methods that they use to actually get there? And they have this overlapping system of measurements. And I spent more time on the explanations of the terms. I don't want to give it too much. I've gone into detail about the methods tons of times. I've interviewed Adam Rees, who got a Nobel Prize because he's so good at this. But close up, astronomers use trigonometry to measure the distance to stars, and it is very, very accurate. You can measure this very carefully. And then the next level is use a thing called Cepheid variable. So there's a type of star that changes in brightness on a variable period of time in a way that allows you to know the intrinsic brightness of the star. You look at how bright the star is, you know how far away it is. That gets you out to nearby galaxies. And then there's the type 1a supernova. This is the one that astronomers are able to use to learn about dark energy. And so type 1a supernova detonate with a very specific amount of energy. You calculate the brightness of the supernova. You know how bright it should have been. That allows you to calculate the distance. And then there are a bunch of other methods. They use gravitational waves to determine the distance to objects. They can measure the light coming from quasars. There's like a whole range. There's about 20 parts to the distance ladder that overlap. And each piece of the distance ladder has been double-checked and double-checked, checked against itself. And so astronomers have gotten very good. And then the final method is they're able to measure effectively the light in the cosmic microwave background radiation and use that to measure how fast that part of the universe is moving away from us, and therefore to calculate how old the universe is. Hope that helps. Did you know that you can watch the same video with no ads and get a bonus question over on Patreon completely for free? We'll call it Q&A+. In this week's bonus question, can small moon impacts be a threat to Earth? And I'll put a link in the show notes. All right, those were all the questions that we had this episode. Thank you everyone who joined me for the live show, everybody who put your questions into the YouTube comments. One, maybe two more live shows scheduled before we go on hiatus. I talked about how hiatus works in the last episode, so check that out. Now, I'm going to direct your attention to one of the people on the Universe Today team who is also producing an enormous amount of content across the internet, and he's just really good, and that's Dr. Paul Sutter. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrea Pedretti, Brian Bodie, Carolyn, Chuck Hawkins, Commander Bailock, Dark Finga, David Gilton, David Matz, Thrall Reading and Math for Toddlers, Evan.Pro, James Clark, Jeremy Madden, Jim Burke, Jordan Young, Marcel Sitz, Michael Purcell, NASA Ocean Guy, Nordspace, OneStepForAnimals.org. Please follow my nephew at VBrick6994, Rain Kaidu, Richard Williams, Sean Sargent, Stephen Fonlemonley, Team 49, Tailslips Canada, Vlad Chaplin, Wolfgang Klotz, and Zelda Fraser will say anything for $100, who support us at the Master of the Universe level, and all our patrons. All your support means the universe to us. So last week I talked about Matt Williams, who is one of the writers on the Universe Today team. And that is just like one little piece of what he does, in addition to all of his sci-fi books, his reporting for other places, his own podcast. And so the other person I want to direct your attention to this week is Dr. Paul Sutter. And he has been a collaborator with me for, I don't know, like a decade. We've gone to Iceland together. We've watched rockets launch. And he is one of the best space explainers out there in the business. He has his own podcast called Ask a Spaceman, but he is a regular contributor to lots of various, you'll see him at space.com. You'll see him at Ars Technica. He did a whole video series for Ars Technica. And he is the celebrity of the Universe Today group. He's the one who you will often see on television shows like The Universe and things like that. So, but what I want to direct your attention to is that Paul is the master of writing these really amazing sort of deep dives into some complex topic that is hard to wrap your mind around, or interesting what ifs. And so he covered a couple of really interesting topics, and he does this sort of style where he does these 4-part series, and he does them on Universe Today. So typically he'll release one 4-part series one week, and then the next week he'll release the next 4-part series. And so the one that he did the week that we just had is like, what if the sun shuts down? And then what is the science that explains what would happen with the light coming out of the sun? And then he previously talked about why, like, what is the evidence for a cyclical universe? And, and what is the evidence against it? And so, whenever he does these deep dives, 4-part multi-series, I think you'll really, really enjoy them. He's got an incredibly accessible writing style and very entertaining. And, he is a PhD particle physicist, so he knows his stuff. So I will put a bunch of links to tons of Dr. Paul Sutter material, so you can go and follow his Patreon, follow his podcast, follow his writing, check out his books, and then, of course, see the series of articles that he writes for Universe Today. All right. We will see you next week.